Relations. There's a lot more about relations later in the course when we discuss relations and functions, but for now we're just dealing with it in the concept of sets. A relation is any set of points that connects two variables. You should be familiar with a Cartesian plane, so that's just the usual xy plane that you draw graphs on. Any set of these points is a relation, and the relation can be described either as some sort of equation, or it could be described in words. For example, if we have the set of points x and y, the set of coordinates, such that y is equal to negative x, that just gives us the line y equals negative x, a line with a gradient of -1 and an intercept at the origin. In other words, this line here. The relation, the set of points such that x squared plus y squared equals 9, this relation represents a circle of radius 3 and centre at the origin. Some obvious points on the circle are points like 3, 0. How do we show that's on the circle? Well, if we substitute x equals 3 and y equals 0 into the equation x squared plus y squared is 9, we get 3 squared plus 0 squared, and that is equal to 9, which shows that 3, 0 lies on the circle. Another obvious point is 0, -3. So x is 0, y is -3. Substitute that in, and we also get 9. A less obvious point would be something like -√8, 1. If we do -√8 squared plus 1 squared, we also get 9. So we have an infinite set of points which would satisfy the equation, and they would be on the circumference of this circle. If instead the relation had been x squared plus y squared is less than or equal to 9, then we're talking about all of the points that are on the circumference or are closer to the centre. So what we would do is do the bounding circumference and then shade inside. If it had been just x squared plus y squared is less than 9, then the points on the circumference would not satisfy the relation, and we'd indicate that with a dashed circumference. Some relations describe an infinite number of points. We've seen some of those. There are an infinite number of points on this line that satisfy y equals -x. There are an infinite number of points on the circumference and within this circle. There are an infinite number of points that are inside the circle when we don't have the circumference included. However, we may have a relation that describes just a finite set of points, such as these 3 points here indicated on this diagram. Now consider the circle and the line on the same diagram. So A is the circle, the set of points on the circumference of the circle, and B is the set of points on the line. What is represented by A intersection B and A union B? Now remember, the intersection is the points that satisfy both of these relations. In other words, on the circle and on the line. So that's a finite set of points, just these 2 points of intersection. So A intersection B is a finite set. It's the 2 points of intersection. And of course, to actually give A intersection B, we'd need to have these coordinates. But we're not going to do that just at the moment. The union is the set of points on both or in both sets. So that's going to be an infinite set. And that will be every single point on the line and every single point around the circumference. I know I've missed the circumference of that bit there. It doesn't matter, you get the idea. So what we could write for that one is that A union B would be the set of points x, y such that x squared plus y squared is equal to 9 and y is equal to negative x. So remember that this or union is an inclusive, so it's all of the points that satisfy this relation, or this relation, or both. In other words, those points of intersection.